Hello everybody. We are going to discuss now a very important point, which is how can we solve problems or equations like these. Now we have four equations and four unknowns, the four velocities and the pressure, if we know the density and the gravity and the viscosity, of course. Then we have these four variables that we want to calculate. But looking at these equations, we can find out that we have four coupled partial differential equations in four independent variables, which is a very, very complicated thing. And solving these kind of equations is not easy at all. So to understand how we deal with these equations, I will give an example with simple cases, just to clarify how we deal with these simple cases and then how this will look like in complex cases like this. So let's as I said, so there are two types of approaches that we follow. The first is what we call the exact solution, and the other is called the numerical solution. To understand, let's see how we deal with this simple cases first. So let's take an example of a simple ordinary differential equation, which is dy by dx equals x squared y squared. And if we want to integrate this differential equation, it will be simply by separation of variables, meaning that we will have x squared dx and then y over y 1 over y squared dy, and then we will just integrate it's the same thing. So we will integrate the equation, so we'll add 1 to this power and divide by the new power, and then the same for here, it's 1 over y power 2 is negative 1 over y, and then we add this c, and this c is the constant of integration. And the reason we have this constant is that the differentiation of a constant is 0. So going from here to there, there is a very, very big possibility that there was a constant that became 0 after we did the integration, the differentiation. So when we integrate, we have to re-put it back here. And let's say we want to double integrate this equation, meaning that this is a second order differential equation, not just a first order ordinary differential equation. And if we want to do this, it's going to be the same thing, but it's twice instead of once. So we will get the answer of this, which is the integral, the first integral, and then we will integrate it one more time. So it's going to be x power 4 over 12, 1 over y is ln y, and then c1y plus another integration constant. So this process or procedure that we followed is called the analytical solution or exact solution, meaning that we start with the differential equation, which is this or this, and with some mathematical steps we can convert it from a differential equation to an algebraic equation. We mentioned this before, that the differential equation is very useful, but we cannot get results out of it. You cannot substitute in this equation to get a relation between x and y. We can do this with algebraic equation, whether this or this. So the analytical solution is the mathematical procedure that we follow to convert the equation from a differential equation into an algebraic equation. Okay, and the good thing about this is that you do this just once. The procedure of converting the differential equation into algebraic equation is done into once, just only once. So if we want to substitute with any value of y, we can just plug it in here and then calculate the corresponding value of x, and the same here. So you don't do the integration every time you want to substitute, you just do it once and for all. And this is a very, very, very big advantage of this. So it's valid for any value of x and y, and as we said, it's done once and for all. So this is the procedure that we follow for what we call the exact solution or the analytical solution. Now comes a question: how can we get these constants, C1 or C2? To get these constants, we need some information about the system that we know beforehand, and this information are what we call the initial or boundary conditions. So the for the first case, C is, as we said, is the constant of integration, and to find C we need to find one valid condition. So we know, for instance, when x equals, let's say 1, y equals 2. So in this case we know a value of x and y that satisfies this equation, and from this we can calculate the value of C. So this relation between x and y is what we call the boundary condition. Okay, and the same for this. If we have two constants, then we need two valid conditions. So we need two values of x and the corresponding values of y for both values of x. Okay, so and of course it's logical that if we have more constants, we will need more conditions. So the number of conditions is equal to the order of differentiation. Now, to differentiate between what we call the initial condition and what we call the boundary condition, it's only about the parameter that we know the condition at. If this parameter is space, meaning that we know a relation between x and y, where x is like x, y, or z, meaning the coordinate, like a space condition, then we call it a boundary condition. If it has to do with time, and let's say this is at time equals 0, x equals something, then we call it an initial condition. Okay, but at the end of the day, they're just relations between two parameters, space or and the dependent variable, or time and the dependent variable, and we need them to calculate the constants of integration. So this is the first approach that we follow. Now for and we agreed before that this is a very useful approach because we can use it once or do the integration once, and then we can apply the equation to any other case later. For there are some limitations to this case. Let's say for this example that we have here, you have a second order ordinary differential equation, and then first order, it's multiplied by x and then axy squared. So in this equation we cannot follow the same procedure. Okay, if you remember, if you have any if you take any calculus class, you would go through a lot of procedures for integration and for differentiation, and for integrating the differential equation from the integral form or the differential form to an algebraic form. And there are a lot of things that you can do in this case, and there are very many approaches that you can follow. And despite all these approaches, there are cases that cannot be solved analytically. For instance, this equation that you see here, at least for my limited knowledge in this field, I don't think that there is a solution to this differential equation. I mean that there is no form of algebraic equation that is result of integrating this equation. So when the analytical solution fails, then we have to go for the other approach, which is the numerical solution. The numerical solution is an approach that we can follow for any case, whether it has an analytical solution or not. And this makes it sometimes a good option for solving like equations like the one we see here. Okay, and the way we solve these equations analytically is simply, let's say this x is the distance. Okay, so we want to integrate this equation in the range of x, let's say from 0 to 100 for instance. Okay, so this is the distance, and y is any other the dependent parameter. Let's say y is velocity, it's the pressure, it's anything else. Okay, so it's the parameter that is dependent on the distance. So if we want to do the integration, then we need to know for the numerical solution, and this is a big difference between the numerical and the analytical solution. For the numerical solution, we need to know the initial value and the final value of the independent variable, or the limits of the independent variable, where it starts and where it ends. And also we need to know the value of the dependent variable, which is y, at x equals x naught. Okay, so this is something that we need to know. And the way it works, or the solution is done, is that simply we break this independent variable, which is this distance, into different increments. We call it steps. Okay, so we break this into many increments. Each one of them have the same distance or the same value. So let's say if this is 100 centimeter, we can break it into 100 steps. Each has a distance of 1 centimeter. or you can break it into 1,000 steps. Each step is 1 millimeter, whatever. It depends on how many steps you want to do the integration for. And what we do is we using some mathematical approaches. There are many approaches that we can do this. There is like a method that's called Euler method. There is Range-Cotta. There are many other methods that we can use to do this. But what we are going to do, whatever this method is we are going to use X node and Y node to calculate Y at X1. Okay, so at the first step, we can calculate Y at this step. And by the knowledge of Y at this step, we can do the same thing. Since we calculated Y1 from Y node and X node, we can calculate Y2 from Y1 and X1, and so on. So you'll keep going one by one until we calculate the dependent variable at the final point. Okay, so it's not like what we did before. It's not doing a mathematical analysis to convert the differential equation into algebraic equation. On the other side here, we do the calculations. We calculate the actual values of the dependent variable at different points of the independent variable, and use each point to calculate the next point, and so on until we reach the final point that we have. Okay, so this approach is valid no matter how complex or simple the equation is. You can apply it very simply without any it's not very simply, but I mean you can apply it regardless of the shape of the equation, and that's why it offers a solution to the problems that cannot be solved analytically. However, there is one very big drawback for this problem, or this approach, I'm sorry, and this is this drawback is that the solution, this YF that we are calculating, is valid only for the initial conditions, which is Y node at X node, and for this range of the independent variable. So it's valid only for X node to XF and for Y node at this this value. So if we change anything, if we change the value of Y node, if we change the range of the independent variable, if we change anything, we have to redo all the calculations one more time. So the solution is only specific for the given conditions. If anything changes, we need to redo all the calculations again. So this is why the numerical solution sometimes is I'd say is not as straightforward, or it's not straightforward and as flexible as the exact solution. The exact solution, as we said, it's done once. You get an algebraic equation and you can apply it many times without the need of doing the calculations again. So this is why or this is the second approach, and hopefully by now you understand the two approaches and the pros and cons of each. Now, how does this relate to what we know about the Navier-Stokes equation and the continuity equation? We can apply this same concept, but on a different level. Now we have, instead of ordinary differential equation, we have partial differential equation. So we have 2, 3, or 4 independent variables. So instead of having x, we have x, y, z, and time. Okay, so now this is getting more and more complicated. So the way we solve this is using software that do these calculations, and they are called the computational fluid dynamics, or CFD analysis or calculations. And the reason is we don't have a way to get an analytical solution of this equation. So we don't have any mathematical method that enables us to convert all these 4 coupled partial differential equations into ordinary or algebraic equations. So the only option we have is the analytical, or I mean the numerical solution. And in this case, the numerical solution, I just put it here. These 2 figures are for 2-dimensional or two independent variables, just x and y. So as we did before here, we broke the independent variable into segments or into steps. We're going to do the same thing here. We're going to break the area into different increments, and each one of them is shape of a triangle. This is a very long story, and there is a lot of things that you need to know if you want to go through this. But my point here is just to show you how these problems are solved. So the area is broken into different triangles. You know, for instance, the velocity at this side. You know the velocity, the pressure here, or whatever the boundary conditions. You know, and the same approach is done. Let's say you are calculating the velocities and the pressure here, and then you use this information to calculate it here, and then this information to calculate it here, and so on until you calculate all the pressures and the velocities. So this is how it's done. So it's not the equations cannot be solved analytically. They can be solved numerically only. Now for what we're going to do in this chapter, we will have we'll deal with very simplified cases of problems that we can solve using Navier-Stokes equation. And in this case, the problems will be very simplified so that we can convert or we can solve the problems analytically. And this is what we're going to do in the coming examples, and we will go through the procedure and how we will solve them. But in general, if we have a problem that is fluid mechanics problem that needs to be solved with all the equations coupled together, there is no analytical way of solving this. The only way is the numerical solution using computational fluid dynamics software. So I'll stop here, and inshallah next time we are going to go through the procedure that we will follow for the problems that we will cover in this chapter, inshallah. So I'll see you then.